Okay, so last time we were talking about chapter 1. Obviously, we talked about significant figures, how to count significant figures. We talked about significant figures in calculations. Obviously, that all ties together with taking measurements and proper measurements. Remember that when you do take proper measurements, you want to always look at the scale of whatever piece of equipment you're using and figure out really what the biggest markings represent and also what the smallest markings represent. And that really will sort of give you an idea as to how far you really can take your measurement. For most cases, you could go one more place to the right of the smallest marking, and that's usually a good way to judge it. And you always want to obviously make sure that you include units. Towards the end last time, we got into sort of conversion factors and equalities. We saw a table, I think, right here. This table, right, is a table of a bunch of equalities. There's obviously others besides what's on this table. But remember that equalities are really just, really the same sort of quantity of a measurement. They're just on different sort of units or different scales. So like we talked about, if you had 100 pennies and $1, it does represent the same amount of money. They're obviously just on different units. There are, when we look at an equality from any equality that we come across, like our 12 inches is 1 foot, we could really write two conversion factors that we could use in conversions. And conversion factors are really just a fraction version of the equality where we put one sort of quantity up on top and one on the bottom. And we could also flip it around and use it in the other sort of direction, such as this. And we use these sort of conversion factors, as we touched upon last time, and really do what is referred to as dimensional analysis when we try to do these type of problems. And dimensional analysis is a way in which we show our calculations, where we show all the units and we show the units canceling, the units that don't cancel, and all those kind of things. The key to it is really opposites cancel. So whatever units you want to sort of get rid of, you need to put the same unit with a conversion factor in the opposite location. So again, if we started with 35 feet and we wanted to know how many inches that is, we would start with our 35 feet. And as we talked about, I think last time, although it's really not written as a fraction, it is considered, really over 1, which really what that tells us is the feet unit is up on top and we want to get rid of the feet unit. So we would want to use a conversion factor here on the left to do so. And if we do that, thank you, we would put the 1 foot on the bottom, 12 inches on top. And basically what we're doing here is multiplying everything that's up on top and dividing by whatever's on the bottom there. And essentially, when we look at the units, when they end up in opposite locations like this, we're essentially dividing feet divided by feet, which basically means it equals 1. And that's how they essentially cancel each other out. Math-wise, what we would be doing is multiplying whatever numbers we have up on top, and we would be coming back and dividing by whatever we got going on there on the bottom. And in this particular case, we really don't have anything going on the bottom besides 1. So that's 35 times 12 gives us something like 420 inches would be our answer. Now, in terms of when we use sort of conversion factors that come from equalities, there are certain ones that are considered exact numbers. This would be one that is considered an exact number. And remember, an exact number is one that is basically achieved by either counting or some type of definition like this, 12 inches is 1 foot. What it basically means when you have something that is an exact number is it pretty much can have as many significant figures as you'd like. And what that really means is when we do a calculation involving one of those things is we sort of ignore anything that is considered an exact number in terms of the significant figures we should end up with in terms of our answer. So if we're really ignoring this guy here, that means really the only number we got to go off of is really the first number that we started with, which has 2 significant figures, which means we should end up with 2 significant figures over here on the right. And I happen to have ended with 2 significant figures, and that would be sort of the correct one here. So it's really important to show, the setup like this. It is something you're supposed to learn and do. And again, that's what's referred to as dimensional analysis. It's extremely helpful, especially if we're dealing with, for example, 2 different units that we might want to convert. If we did like say miles per hour, right? If we're driving 75 miles over an hour, and we want to convert it to something like meters per second. By first setting up your calculation like this, where you can clearly see it, exactly, where you should put the opposite units. Bless you. We should go, somewhere from miles, which are up on top, and hours. We know that we should do a mile on the bottom, whatever you want to use, kilometers, meters, and the miles will cancel. We also can clearly see that hours are on top, which means if we want to get rid of hours, we do need to go hours. I'm sorry, hours are on the bottom there. We gotta go hours up on top, and that would be 60, say, minutes. And we could do our conversions really well. So keeping your units really separated as sort of up and down, it really does allow, thank you. It allows that you to clearly see where you should put it. It's a very common error when people have maybe multiple units as they're trying to convert, and they don't really sort of set it up like this where you could clearly see the units canceling and not canceling, is they very commonly multiply when they should be dividing, or dividing when they should be multiplying. So if you keep everybody sort of separated and up and down in terms of the units, it's really helpful in sort of solving them. Any questions on any of that stuff there we were talking about last time? Okay. So let's talk about actually solving these type of problems. And there's a few different steps along the way that can be very helpful. First off, it's sometimes helpful to write what's sort of given to you in a problem. And really in any type of problem, besides just conversion type problems, it's sometimes very helpful to write, what is given. You want to write what you want to find. You want to think about sort of your pathway to get you to where you're trying to go. And that usually will involve thinking about what type of equalities would be helpful to do that. Obviously, the appropriate conversion factors from those equalities. You should set up the problem in terms of showing the units like I just did a second ago, where we can see all the units canceling, what doesn't cancel, and what's left over. And clearly, you should solve the problem to the correct number of significant figures. Just going back for just a second in terms of looking at this sort of exact number, remember that when we do pull conversions that technically come from English to English conversions like this one here, or even metric to metric conversions, they are technically considered exact numbers. When you do cross over, like in this chart on the far right here, from metric to English sort of conversions, you should look at normally the significant figures that are in those conversion factors when you do a problem, except for like the one that's circled here that we talked about, I think the other day. That's considered still an exact one, even though it's metric to English, but other ones you should look at it. And when we do, for example, look at a conversion factor like this and trying to determine what one you should look at, you should actually look at the one that actually is a number, not the one that says 1. So you would ignore the 1, that's kind of an exact number. But in this case, we would look at the 0.621 and say that has 3 significant figures, and use that when we are making our judgment as to how many significant figures our answer should have. So that's the one place where if you run across a conversion factor, technically English to metric conversion factor, you probably should take a moment and look at the significant figures. In a lot of cases, it will still most likely be the original number you started with, but occasionally it might not be, but in a lot of cases it will be that original number. But English to metric, you should take into account the significant figures that are there. Any questions on that? Yeah, so let's take a look at one here and see how we do. All right, we go to the AM PM and get a 32 fluid ounce drink of Diet Coke from the Thirst Oasis. How many gallons of Diet Coke did you drink? We'll give you some qualities that might be helpful to get you there, and some equalities. All right, so take a moment or two to see what you come up with. We want to get to gallons. So again, you could look up on a a conversion sheet or a quality chart there. And our pathway here is to go from really fluid ounces to quarts and then quarts to gallons. These are our equalities. And again, as we talked about, from any equality, we could write two conversion factors. So for example, we could write 1 quart over 32 fluid ounces. Or we could do 32 fluid ounces over 1 quart. And obviously from our quarts and gallons, we could write 4 quarts is 1 gallon. Or 1 gallon is 4 quarts. Again, as we talked about last time, we will not use obviously both of them in our problem. We just want to do our opposites. So given to us here is 32 fluid ounces. So that is where we want to start, 32 fluid ounces. Again, you could think of it as being a fraction, even though it's not written like that. That tells us that fluid ounces are on top. And again, it is opposites that will cancel that for us. So we do need to use the conversion factor over here on the left, as that has our 32 fluid ounces on the bottom and 1 quart up on top. If I laid up the calculation right here, the units I'm in are quarts, right? As the fluid ounces would cancel each other out. If you want to get an answer in these type of conversion problems, you can, or the other option is you could just continue on with the calculation. And that's what I'm going to do here. Again, by setting it up like this, I could clearly see my quarts are up on top, which means to get rid of quarts, I need to put quarts on the bottom. And that would mean that I would need to use, in this case, the conversion factor on the right-hand side for our second one. Continuing on here, the 4 quarts will be on the bottom. The 1 gallon here will be up on top. Same thing here, really quarts on top divided by quarts on the bottom. That's going to cancel out our quarts. Any questions on that so far? We're going to multiply everything we got going on here on the top. Again, we're then going to come back and divide by everybody that we got on the bottom. Here we really have 32 times 1, which you don't really need to put the ones. Hit equals, then divide it by 32, hit equals, divided by 4, hit equals, and you will end up with 0.25 gallons in this particular case. And that is the answer. The answer is not 1/4. Because that makes me think you're too lazy to divide. Yeah, so don't leave any answer in a fraction, divide it out. Not a bad example there, but I've had people write something as an answer like, 323 miles over 4,250 hours and just circle it. So, don't leave answers like that. Actually divide it out and get a number. Any question on any of those steps? Really, our guys in the middle there are sort of exact numbers. So we started with 32, which is 2 significant figures, and obviously ended with 2 significant figures at the end. Yeah. Yeah. Now, we do have 2 things that we were dividing by on the bottom. Again, I think we might have talked about earlier in another day, but if you have multiple things that you want to divide on the bottom in a situation like this, and you want to for sure get the right answer, the way you would want to do it on your calculator is you can multiply as many numbers as you want on top. You should hit equals at that point. You should divide by the first number and then hit equals, divide by the second number and hit equals, and you'll always get the right answer. If you try to put it all in at once and you do it correctly, you'll be okay. But if you try to put it all in at once and you don't do it correctly with parentheses and stuff like that, you might get the wrong answer. So almost a foolproof way of doing it when you have a situation, you have multiple things to divide by on the bottom. It's just keep hitting equals after each one and divide by each one individually. Other questions? Yeah.
With the calculator up there, what I was wondering if there's any way you can show it how to plug it in on the calculator.
Let's see. So let's see. I don't really have a way to actually do that, but here's exactly how you should punch it in. Basically, you're going to take 32. And if we had numbers on top, you can multiply it by each of the numbers. And at that point, you should hit equals. And then we're going to divide by the first number on the bottom, which is really 32. So at that point, you would hit the divide button and 32 and then hit equals again, and then hit the divide button and 4 in this case, and then hit equals again. And that would be the right way to sort of punch it in. And it's a really good way of doing it, especially when you got multiple numbers on the bottom. I've seen it a lot of times where people, they try to put it all in at once in their calculator and they end up getting the wrong answer. So typically this way, if you kind of go individually by everybody that's on the bottom and hit divide equals, you'll usually never get the wrong answer. You don't have to worry about the stuff on top because it's just multiplying. So you can just multiply everybody to the end and then at that point hit equals. Other questions? Okay, so let's try another one here. All right, during surgery, a patient receives 5 pints of plasma. How many milliliters of plasma were given? Here's some equalities that would be helpful. All right, well, let's take a look. So same idea. We're starting with really units of pints and we want to get them into milliliters. So we could look up some equalities. One pathway would be, again, here and now to go from pints to quarts, quarts to our milliliters. Just like before, we could have our 2 conversion factors for each of these guys. Our 1 quart here, 946 milliliters. So here we are given 5 pints, so that is where we want to start. Again, not written as a fraction, but that should tell us that really the units of pints are up on top. So that makes it really easy to determine that we should go opposite of that here using the conversion factor over here, which gives us 1 quart up on top and 2 pints. Again, at this point, you could get an answer if you wanted to, or just continue on. But regardless, at this point, the pints would cancel each other out. We would be left with quarts, which is close to what we need. We then need to go to milliliters. Again, clearly seen here in this case, quarts are still up on top, which means to get rid of it, we got to go opposite, which means we need to use the conversion factor there on the right. And if we do that there, that's a 946 milliliter up on top, a 1 quart on the bottom. At this point, the quarts will cancel each other out. That leaves just the units of milliliters, which is good because that's what we want. It's on top. 1 unit on top is what we need. And here we're going to take basically 5 times 1 times 946, hit equals. We're going to divide it by 2, hit equals. You can divide it by 1, but nothing's going to change. On our calculator, we get laid up to us 2365 milliliters. Significant figure-wise, where should we end up with? Well, in this particular case, we wouldn't look at this as that sort of English to English type conversion. That's exact. This is actually a crossover one, which technically we should kind of take a peek at it, and that has 3 significant figures. Our original number has, though, 2 significant figures. Pretty much in all these conversion problems, we're pretty much only doing multiplying and dividing, which means we could look at significant figures, and it is the one with the least number of significant figures, which means we really should end up there at 2 significant figures, which takes us to there. We look at the number after it, which is a 6, which means we probably want our factor up there to 2400 milliliters. You could also, if you wanted, write it in scientific notation as 2.4 times 10 to the 123 milliliters. Yes, good. It goes to the type of conversion factor that you're using. So if it is a conversion factor that's basically between like English and English, like quarts and pints are basically English to English sort of conversion, that's considered an exact number. If you're looking at a conversion factor that is like a metric one to a metric one, that also, for example, like milliliters to liters, that is also a exact number. If you have one where it crosses over from like metric to English, like technically a quart is kind of English unit, milliliters is a metric unit, you should look at those. So that's why we looked at the 946. And out of that conversion factor, it will usually have one of them that's a one, you know, like the 1 quart. We don't look at the one, but we do look at the 946, and that would have 3 significant figures that we're basically multiplying by 5, which has 2 significant figures, and that's why we ended up with 2. Yeah. Yeah. Yes, sir. Why did I put the box over it? Is that what you're asking? Yeah, so if your question is, we used this conversion factor, we had a choice of these two for that part of the calculation, which was right here. We used the one on the right there because that's the one that will actually cancel out the units we did not want to keep. So right before that step, we had this unit up on top, the quarts. So we basically wanted to get rid of the quarts. So because the units of quarts are up on top, we had to use the conversion factor on the right because it has quarts in the opposite location on the bottom. And the reason for that is essentially, if we just look at the units, what we're essentially doing is we have quarts on top and we're going to divide it by quarts on the bottom, which means it basically equals 1 or it cancels out. So that's why we kind of go opposites. It's the same thing that we basically did with the pints. We had the pints that technically was on top, and we divided it by the pints that were technically on the bottom, which is why we chose this conversion factor here originally for that part of the process, so that we could get the pints basically to be divided by pints and cancel out. So we want to choose a conversion factor again in sort of the opposite location. And, you know, even though it's sort of words, for example, it's the same idea. If you took 2 divided by 2 would equal 1. When you take like a quart divided by a quart, it basically equals 1 and cancels out. Other questions? Yes. You should always give the answer to the proper number of significant figures. I will say probably 9 times out of 10, if you're doing a conversion problem, like what we're doing here, just kind of converting units to some other units, it's almost a safe bet. I won't say 100% of the time, but pretty close. It's almost a safe bet that original number that you're starting with is probably the right number of significant figures for your answer. It's not 100% proof, but that's why you really should look. So when we look in terms of significant figures on this one that I keep scribbling on here, but really there's only 2 numbers of interest. It's this one we should look at. And because this happens to be an English to metric conversion, we should look at the one over here. And really, we want to look at what we're doing with these numbers, which is basically multiplying, right, and dividing. So we want to look at the significant figures. Thank you. So we would look at this guy, which has 2 significant figures, basically times 3 significant figures should yield us 2 significant figures. Remember, it's always the one with the least number of significant figures is what you're looking for in terms of your answer. Yeah. Yeah, so you also look at everything. A lot of the conversion factors are ones you could really ignore because they're exact numbers, but occasionally you will come across, obviously, like we did here, one where it is a sort of English to metric, or it might even be a conversion factor that you actually get from the problem itself, which isn't like a true conversion factor, it's just specific for the problem. You should look at that as well. All right, let's take a look at another one here, see how we do. All right, you're stranded 125 miles away from home. You have no money. You decide it seems like a nice day for a walk. If you walk an average of 55 feet per minute, how many days will it take you to get home? Well, you never know. Maybe packed well as that happened, right? By the way, there are 5,280 feet in a mile. That might be helpful. There you go. All right, fine. You're stranded. You don't have a cell phone. You don't know where your car is at. Yes, because you were thinking ahead, like, I know I'm going to always leave my cell phone in the wrong spot, but I'm going to bring some food because never know when you get hungry, I suppose. And yes, you're walking with a tent and all the other supplies that you need. away from home. We are walking 55 feet per minute. We want to know really how many days it's going to take us. So we got a couple of things happening here. We have 125 miles, which is obviously like a length or distance, if you will. We have 55 feet per minute, which is really a rate, right? And a rate is kind of how much you do something in a certain period of time. In this case, how far we're walking in a certain period of time. It is the rate that's really going to allow us to convert it from really distance to time, right? Otherwise, we can't get the time, because this is the only guy that basically has time associated with it. And we eventually want to end up in days, which is obviously. We do also have a problem in terms of units. One distance is in miles, one is in feet, which means they will not cancel out using them exactly the way they are written. We have to do actual conversion, get them into the same units. And you could choose to do the feet to miles, or you could choose to do the miles to feet. So what I'm going to do is I'm going to choose to convert the miles here into feet, so I could just use my rate the way it's written. And to do that, we could use our equality here. And if we did, we would have 125 miles using our conversion factor there. 1 mile is 5,280 feet. Our miles cancel, gives us something like 660,000 feet, hopefully packed light as I'm carrying them. The good news is we now have our distance in feet, which matches the units that we see here in what was given to us in a rate. This guy actually came from the problem, and it's not a really for sure rate in the sense of it's always going to be 55 feet per minute. It's actually a conversion factor that we get problem. And we could actually treat it like a conversion factor. We could use it just like it's written there, 55 feet over a minute, or we could use it in the opposite way, a minute up on top and 55 feet on the bottom. And in this particular case, we're going to continue on here with our 660,000 feet. I need to go opposite of feet, which means feet should go on top or bottom. Should go on the bottom, which means we're really going to use that sort of rate in the opposite direction here. We're going to do a minute up on top and 55 feet on the bottom. By multiplying our distance in the correct units by our rate, or really dividing by our rate, our feet will cancel. And at this point, we are left in just minutes at this point, which is good because, again, we want to end up in days, which is a unit of time. Question so far. What is really left at this point is minutes. So all we have to do now is convert minutes to days, and you could do it a couple of different ways. We could know that in 1 minute, actually there are, I should say it right, there are 60 minutes in 1 hour, right? That way the minutes will cancel opposites of each other. There are how many hours in a day? Yeah, there's just 24 hours in a day, not 60, 24 hours in 1 day. Again, we want hours up on top, so we need hours on the bottom so that they properly cancel each other out. And now we are left with just days. So we can multiply across the top here. So 660,000 times 1 times 1 times 1, basically, and hit equals. We're going to divide by 55, hit equals. Divide by 60, hit equals. Divide by a 24, hit equals. And we end up with 8.33 days. All right, it's gonna be a long walk, right? Any questions first off on that? We'll go there first, yes. It's not necessarily supposed to be 2 significant figures. Was that your question as well? Okay, so let's talk about the significant figures here. By the way, on your calculator, it's 8.3333, a whole bunch right threes. So when we look at what we did here and sort of what we used to get there, this is, an exact number, right? There's 24 hours in a day. That's obviously an exact number. So in terms of significant figures, we don't have to look at any of those numbers that are there. This is really a conversion, but it's not I'll say it this way, I guess it's not a legitimate conversion, like, 12 inches is always a foot, no matter what the situation is. This is really specific for this question, which means we really should look at the number of significant figures here. This technically is 1 minute, which is an exact number, the one, but this would have 3 significant figures, right? The original number, not really this number, but the original number that we started with back here had how many? 3 significant figures, which means pretty much everybody had 3 significant figures. That's why my answer here should have 3 significant figures in this case. Yeah. Yeah, we wouldn't usually answer it like that, even though technically, you could figure out what 0.33 of an hour is, and that type of stuff. We would probably leave the answer like this in a decimal form and just leave it at 8.33 days. Was that the same question, or was there another hand? Yeah. Yeah, so 24 hours in a day, again, is considered an exact number, so you wouldn't look at it at all in the consideration, nor with the 60 minutes. You basically just ignore it. The truth is they could have as many significant figures as you want, and because of that reason, in calculations, we ignore it, because I might go, hey, I want to give it 3, you might want to give it 4, and then we'll have some different answers. So the rule is we sort of just ignore anything that's considered an exact number in terms of trying to help us decide how many significant figures we should have. And what that usually leads you back to in a lot of cases is sort of the numbers that you see in the problem. And you could kind of look at those numbers and go, okay, those, in this case, they both had 3. And that's really where we should end up. And a lot of just straight conversion problems, if you're just like taking, like I said, a number and just changing the units, most times is going to be probably the same significant figures you started with would probably be the right number. And again, not 100% time, but pretty close. But you should definitely, in this case, we should look at really this conversion, and we should be looking at the 55.0 part of it as, how many significant figures, because it's not like a conversion you would find in a table, like 12 inches is always a foot. Other questions on conversions there? Okay, so let's see here. What happens if we had, let's say we were driving 75 miles per hour and we wanted to know how many feet per second that was. And again, 5,280 feet in 1 mile, and see what you come up with. And then also, why don't you try one more here? Why don't you try if we had, let's say we had 325 cubic centimeters, and we want to know how many cubic feet that would be. And a couple that will help you there. 1 inch is 2.54 centimeters. And then obviously 12 inches in 1 foot. All right, take a few minutes here, seconds. And the key to doing this correctly so you don't screw up on multiplying and dividing the wrong thing is to keep everybody in their proper location. So we will start with our 75 miles. And by the way, when you have something like this, usually the number stays with the top unit and is per 1 of the bottom unit is basically what we're doing there. I'm going to start with the miles conversion. So I could clearly see my miles are up on top. So if I want to get rid of my miles, miles need to go on top or bottom. It does need to go on the bottom here, right? Miles are starting on top. So I got to put my miles on the opposite side like we were doing before. And I need to go 1 mile on the bottom. 5,280 feet up on top, just like we did before. If we stop right here, the miles will cancel. And if I stop right here, what are the units I'm left with at this point? I am left with feet on top per hour on the bottom. Yeah, so we just successfully did the feet part of it, right? Now what's left is we need to take the hours to seconds by clearly writing it like I did here. I can see my hours are on the bottom, which means my next conversion should have hours where? Should have hours in the opposite location, which means hours should go on top. And I could know that in 1 hour, there are 60 minutes, right? That will cancel out the hours. And if I actually stop the calculation right at this point, I'm in units of feet on top per minute, which is close to what I want, but I do want seconds. So I got to do one more conversion here. Again, I can clearly see where my minutes are. They're still on the bottom, which means to get rid of them, I got to put minutes up on top. And we know that in 1 minute, there are 60 seconds. The minutes will then cancel. The units that we're left with are feet up on top, seconds on the bottom, which is what we are aiming for here. Question on that there? We're going to multiply everything we got there up on top. So that is going to be 75 times 5280. Everything else is 1. So I'm going to hit equals. We're going to divide by 60 and divide by 60, I believe. And we end up with 110 feet per second. That was a pretty good guess of just making up a number. And in this particular case, is that the right number of significant figures? It actually is, right? We should actually have 2 significant figures based off of which number? Yeah, everything else here, exact number, don't have to worry about it. So we would go back to our original number there, which was 2 significant figures, and we end up with 110 feet per second. Any questions on that there? Very important to set it up like that. I can't tell you how many times I've seen people try to do a problem just like this, and they end up multiplying the 60s up on top because they don't know where the unit is. So you want to clearly keep those units where they should be, up or bottom, and that makes it super easy to figure out how to cancel out what you need. Any questions on that particular one? All right, looking at the bottom, we got cubic centimeters to cubic feet. When we cube a distance or a length, that actually is a volume, right? So that's actually volume measurements we're looking at here, but they really are coming from length measurements, which is why we have these conversions over here. So we could go from centimeters really to inches, inches to feet that are cubic because it is cubed. So if we start with 325 cubic centimeters, I could do my conversion of centimeters to inches. Centimeters should go on the top or bottom? Should go on the bottom so that they cancel. By the way, if I do this conversion just like this, does it completely cancel? It does not. It's only 1 centimeter. That's 3 centimeters, right? It only takes out one of them. You actually have to do this conversion not once, not twice, but actually 3 times to do it properly. 1 centimeter, 2 centimeters, 3 centimeters, take out all 3 of those cubic centimeters. Inches times inches times inches on top give me cubic inches, yeah, up on top. Which means I can now go from cubic inches to cubic feet by using this, which technically I need to do not once, not twice, but also 3 times to make sure it properly cancels. And in this case, we want to actually get rid of inches. So inches are going to go on the bottom. 12 inches is 1 foot. One more time. 12 inches is 1 foot. And lastly, 1 foot is 12 inches. Inches times inches times inches on the bottom gives me inches cubes, which takes care of 1, 2, and 3 of them up on top, leaving me feet times feet times feet, which gives me cubic feet, which is what I'm going for in this particular case. Do you have to write it all out with all 3 of them? You don't, but it might be a good idea because I can't tell you how many times I've seen people do something like this and never actually cube the number inside, just write it, but they actually never do the math right. So although it takes a little bit more room, you will probably not forget to do the math right, but you technically can write it like that in place of these three here. And same thing with this, you can do the same thing here. But just make sure you do the math actually 3 times, but it's a very common mistake. People will write it and actually not do the math part. So if we're going to do the math, we're pretty much 325 up there on top and everything else is dividing. So divide by 2.54, hit equals, divide 2.54, hit equals, divide 2.54, hit equals, divided by 12, hit equals, divide by 12, hit equals, and one last time, divide by 12 and hit equals. We end up with 0.0115 cubic feet in this case. 3 significant figures because original number. This is one of those. 1 inch is 2.54 centimeters, an exact conversion, which means it's an exact number. And obviously 12 inches to 1 foot is a English to English conversion, also an exact number, which leaves us again our original number to look at, which is 3 significant figures. Any questions on that? That's a very common one, and sometimes people come across and they really do forget to kind of do it 3 times per se. And again, even if you write it like the top right there, make sure you actually do the math 3 times. Questions on conversions? Yes. Okay. Good times on conversions. There we go. All right, the next thing we're going to talk about is something density. So density can be defined as the amount of matter that's present in a given volume of solution. Density of an object is basically mass volume, the mass divided by volume. Differences in densities determine whether or not, for example, an object will sink. So if we put an object in water, the differences in density will determine whether or not it will sink or float. If something is more dense than liquid water, it will sink. If it's less dense than liquid water, it will float. You could also have some differences in densities of liquids if you just put them like in a container. They will separate out based on densities, and you'll see probably some different layering happening. The most dense liquid would be the one at the top or the one at the bottom. Yeah, that would be more dense down here and less dense up here. You drop something in there and it just kind of floats in that layer. That means that thing is more dense than everything above it, right? But less dense than everything below it, right? Which is why it's floating in that part of the solution. There is a formula for density to which we calculate, and the way you calculate density is mass divided by volume. And that is a formula that you do need to know. So D is equal to M divided by V. If you wanted to solve for volume, you would multiply volume to the other side, divide by density, and the volume would equal the mass divided by the density. If you're looking for mass, you would just multiply the volume to the other side, and mass would be volume times density. Sometimes people remember this by the wonderful DMV triangle. Everybody loves the DMV. Unless you have to go to the DMV. Density is mass over volume. Volume is mass over density, and obviously mass is density times volume. So that's a good way you can kind of remember it if you like. Typical units of density for solids and liquids, which is pretty much what we deal with mostly in this class, are grams per milliliter, are grams per cubic centimeter. Same idea as what we were just talking about. The number will usually stay with the grams and is per 1 milliliter or 1 cubic centimeter. If you remember, a milliliter is kind of the same thing as a cubic centimeter. It's a 1-to-1 conversion. So they're basically the same in a sense, just difference. How do we get some of those volumes? Obviously, the milliliters we could get by just taking a volume reading in some type of cylinder or something like that. We can get something like cubic centimeters by taking something like a cube and measuring the length times the width times the height, which each one would be measured in centimeters, which if you multiply them all together gives you cubic centimeters, which again is a volume. So a very common way you can kind of get the volume of something like a cube is you take a ruler out, measure the length times the width times the height, multiply them together, gives you the cubic centimeters. For gases, and again, we don't really get too much of the density of gases, but typically they are given in grams per liter, but these are probably the two common units that you'll come across for density. So you do need to know the formula for density. You do need to know how to rearrange it properly. Any questions on that so far? Okay. So that's diet 7-Up and regular 7-Up. Why does the regular 7-Up sink and the diet one floats? Yeah, so the regular is a good party trick, by the way. You could ask people, are they both going to sink, both going to float? Actually, the regular soda will always sink because it has a lot more sugar, weighs it down. Diet sodas have artificial sweeteners, less of it in there, and it typically will float. Again, good party trick in case you need something to entertain your guests. There you go. Some densities of common substances. One number that we use a lot is the density of liquid water. Is usually 1 gram per milliliter or 1 gram per cubic centimeter. Density does change with temperature, but if all things are considered and you're doing a problem and you actually need the density of water, it's a pretty safe bet just to use 1 gram per milliliter unless they specifically give you a different value. But density really does change with temperature. One sort of unusual property of water is when it is in the solid version, it is actually less dense than the liquid version. Most things are actually more dense in their solid phase than their liquid phase. We know that because when we put ice in our drink, it ends up on the top, right? It floats to the top ice. Well, if you provide you don't put too much and you weigh it down, you do a nice even layer of ice, not overwhelmingly. The ice will float to the top. And that'll be refreshing on your 8.3 day walk with all your stuff. And the reason for that is actually, we'll talk about in a later chapter, but when water freezes, what ends up happening is the water molecules don't get really so tight to each other. They create a lot of open space between the different water molecules. And if you think about density, which is mass over volume, by creating all this extra empty space, the volume part gets a bigger number. Small number divided by big number gives you a smaller number. So ice actually is less dense than liquid water. All right, let's take a look at an example here. A block has a volume of 25.3 cubic centimeters. It has a mass of 21.7 grams. Calculate the density here of the block. Density, so we want to think about our density formula, which is mass divided by volume. Not just in these problems, but in problems throughout chemistry. It's usually a good idea to label and think about what's given to you. We have a cubic centimeter, which is a volume. We have 21.7 grams, which is a mass. So clearly here we have both of the things that we need. So the density in this case would be 21.7 grams divided by 25.3 cubic centimeters, giving us a number of looks like 0.857707509 units are grams per cubic centimeters here because the units do not cancel. And clearly I gave way too many numbers. Yes, the actual number of significant figures we should have should be 3. We're dividing here, right? 3 divided by 3 should take us to here. So we should really trim this down to 0.858. Looks like, again, grams per cubic centimeter. Number stays with the grams part per 1 cubic centimeter on the bottom. Any questions on that one there? Okay. Now, as I mentioned before, 2 very common ways to get a volume is just simply taking a volume reading, measuring a solid. Another very common way to sort of get a volume, especially done with density, is what's known as volume by displacement. Volume by displacement basically means that if you take some liquid like water and you put a solid object in it, so if we take something like a graduated cylinder here, wonderfully drawn, with an initial volume, and we take a solid and we put it in there, what will happen to the liquid level when the solid goes in? Will it go up or will it go down? It will go up, right? And that will give us a final volume. And this is what is known as volume by displacement. So the difference in the two volumes there will equal the volume of the object. So the volume of an object is the final volume minus the initial volume. And that's what we see here before she takes a dive into the tank. We have a certain initial volume. She dives in, she will displace a volume equal to her ohm. And obviously, if we take the difference in the water level there, that will equal her volume. Hopefully that's not just markings, but a ladder so she could get out, I hope, and she's not trapped in there. So that is a very, very common way and a very easy way you can figure out the volume of a solid object. Is just very drop it in some water and take some initial and final readings of it. So let's take a look at an example like that here, I think. There we go. A student fills a graduate cylinder with 25 milliliters of a liquid. She then tosses a solid in it. The volume rises to 33.9 and the mass of the solid is 63.5. What is the density of the object? All right, let's take a look. So again, we're obviously dealing with density. So we want to think about our formula here. We clearly have the mass given to us, which is good. We do have a couple different volumes. So again, what's happening here is what we just sort of drew on the other page. We have a graduated cylinder here that's starting out at 25 milliliters. We're going to take our solid, which weighs 63.8, 63.5. We're going to put it in. When we do so, our graduated cylinder is then going to rise to a level of 33.9 milliliters with our solid in there. At this point, we do need to find the volume here by displacement. So the volume of our object here would be our final volume minus our initial volume. And that would be our 33.9 minus 25.0 milliliters. That's going to yield us an 8.9 milliliters, if I'm not mistaken. And that will now be the volume part of what we need. So now we do have the mass and we do have the volume. We can now actually calculate the density here. Density would be our 63.5 grams divided by our 8.9 milliliters. So 63.5 divided by 8.9, that's going to get us a 7.1 grams per milliliter. Again, the number stays with the grams part and is per 1 milliliter. We ended up on two significant figures because yeah, so we did a couple of things in this case. We actually first subtracted, right? So we do want to make sure we go to the proper number of decimal places, which is 1 decimal place in this particular case. Although we went to 1 decimal place here, this actual number does have 2 significant figures, which is important because the very last math that we did was dividing, where we divided 3 significant figures divided by 2 significant figures, which obviously yielded us 2 significant figures in our answer. So this is a case, and as we talked about, you may do multiple steps along the way. You want to kind of keep track of everything and then obviously clean it up to the end. If you just strictly looked at the numbers in the problem, for example, you might end up with 3, which would be incorrect in this case because of the math step that we did. So you want to kind of follow along as you're doing it and keep track of it. Any questions on that there?